Hello. Today we're studying hypothesis testing. Let me give you a scenario. Imagine that you apply for a job and your job is to pick stocks for a financial company. And you tell the financial company that you can tell whether or not a stock's going to go up or down with 70% accuracy. So you're right 70% of the time. So they go through all of your application and interviews and everything's good. And they say, now for the final test, we're going to give you 10 stocks and you got to tell us whether they're going to go up or down. So you make your predictions on those 10 stocks. And then they wait for a week and three of those stocks you're correct on. So you've claimed that you're correct 70% of the time, but you've only been correct 3% of the time. So should they believe that you're actually correct 70% of the time? The first thing you might think is, well, obviously you should be correct 7 out of 10 times. But we know that, you have good luck and bad luck. For example, if I was going to flip a coin 10 times, you would expect me to get 5 heads and 5 tails. But I could get 4 heads and or 6 heads. And you wouldn't think, oh my gosh, there's something wrong with this coin. You would just think, oh, it's just weird luck this time. Similarly, if I said I was 70% accurate and I got 6 out of 10, you might say, yeah, that's pretty close. Maybe it was just bad luck. If I got 8 out of 10, you might also agree with that. However, this is the beauty of statistics. We don't have to be ignorant anymore. We can actually calculate what the probability of getting 3 or fewer out of 10 tries is if we're 70% accurate. Okay? So, what we want to look at is the probability of 3 or fewer, in other words, of doing at least that bad or worse. So, we can do that. We type in, actually, I'm going to let you do that. If you're 70% likely to get something right, you try it 10 times, what's the probability you get 3 or less successes? All right, so that's just the binomial distribution. We've done it before. So it would be binom.dist. 3 is the number of successes. 10 is the number of trials. 0.7 is the probability of success. And true because we want 3 or less. And if we type that in, then we get 0.01, so about 1%. So if somebody is actually accurate 70% of the time and they try 10 tries, about 1% of the time they're going to make 3 or fewer correct. Okay? Now, we might say, okay, look, it's possible that you're actually 70% correct and just got super unlucky, but there's really only 1% chance that you would be this unlucky if you were really that good. And in this case, we might not want to hire the person, which I guess is you. So let's take a look at what we've actually done there. What we've said is, let's assume that the thing you're claiming is true. And then we're going to see how unlikely what we've actually observed is if that thing is in fact true. So we're assuming that 70% is the true number, and we're going to see how unlikely the thing that we observe, which is 3 out of 10, is if the 70% is true. And we say it's very unlikely, and therefore we're going to reject the notion that the correct answer is 70. That's how we're going to do hypothesis testing. We're not normally going to use the binomial distribution. We're going to use the t-distribution, and there's going to be some steps. And I'm going to go through the steps, explain each one of them, and then I'm going to go through them again, and then I'm going to give you problems and ask you to go through the steps. So the first step is we need to specify something called alpha. And alpha looks like this little guy up here. It's the Greek letter, the first letter of the Greek alphabet. And this is what we call the significance level. Typically, we would specify alpha to be 5%. And what that means is if the probability of this thing happening by chance is less than 5%, then we're going to believe that it's not chance and the claim we've made is false. So for example, there's a 1% chance that somebody that was 70% accurate would only get 3 out of 10. That's smaller than alpha, so it would reject it. On the other hand, had they gotten 5 out of 10, there's a 15% chance that they would have gotten 5 or fewer out of 10. So that wouldn't have surpassed our alpha threshold. It's bigger than alpha, and so we're like, 15%, we can live with that, but we can't live with anything that's 5% or less. Now, alpha doesn't have to be 5%. That's just sort of the default value of alpha that most people use, which means that you're going to make what's called a type 1 error. And what this means is that we reject the hypothesis when in fact it's actually true and it was just bad luck. So basically, we're going to say, is it bad luck or is our assumptions flawed? And sometimes our assumptions are flawed, but sometimes it's just bad luck. So for example, maybe this was that 1% of the time when the person who actually was really good at picking stocks messed up. So that would be a type 1 error. So this person's true value is 70%, but they just had really bad luck on their test. And we said that no, the 70% is wrong, and that's a type 1 error. A type 2 error is the reverse, when we say that they're not wrong, but they actually are. That would be if they had good luck in this particular case. Okay, so the first thing is we specify alpha. You can specify it at anything, but some common numbers are 10%. So we will make a type 1 error 10% of the time. 5%, so that's 1 out of 20 times, or 1%, so 1% of the time we're going to say, yeah, we don't believe this, even though it might actually be true. But typically 5% is the default. Okay, the next thing we have to decide on is whether we want a one-tailed or a two-tailed test. Again, the default is usually a two-tailed test, but let me talk about the one-tailed test first. For example, this situation with the person who claimed 70%, we would not be worried if they got 10 out of 10 correct. We're only worried if they're in the bottom tail, right? So we're only worried if they get too few correct. We don't care if they get too many correct. So that's a one-tailed test. You could have, and conceptually, if you draw a distribution, what you're worried about is only the probability that it's in one of the tails, and you don't care if they do better in the other tail. We can have one-tailed test in the other direction. Say we have a part that is failing 30% of the time, and you want to know, and you get a replacement part from a new supplier. You're only going to be worried if it fails more than 30% of the time. If this replacement part's failing 20% of the time, you don't care if that's unusual. But if it's failing 50% of the time, then you start getting concerned and saying, is this just a bad luck, or is this new part worse than the original part? But mostly what we're interested in, that, like I said, the default, I shouldn't say even mostly, the default value is typically a two-tailed test. And we're really worried about whether or not something is very far from what we're expecting. So here's an example. Say that they raise the federal minimum wage to $15 an hour. And you're paying minimum wage now, which is, I think, $7.50 an hour. And here's your question. If this changes the number of hours people want, you're going to have to hire more people or lay off some people. And you're really curious whether it's going to change the number of hours. Now, it could make the number of hours people want to work go up, because it's, you're getting $15 instead of $7.50 to work another hour. People might want to work more hours. On the other hand, you can work the same number, you can work less hours and still make the same amount of money. So if people are shooting for a fixed amount of money, they may say, hey, I will take more leisure time. If they're shooting for how best to spend their time, they may want to work more hours. You don't really care whether it's more or less. You just want to know if it changes. People may also sort of stay the same. Say, yeah, I'm just going to work the same number of hours, but just make more money. Okay? So in that case, it's a two-tailed test, because you don't care if it's too big or too small. Okay? Now that's the default, typically, is a two-tailed test. Now, when we have a two-tailed test, it looks like this, and we have our alpha value. So if our alpha value is 5%, then that means we want 2.5% in each tail. Okay? If it's 10%, then we want 5% in each tail. and we're just concerned that things are further away from where we expect them to be. And I'll explain a little bit more what that means in a second. So now we've specified how precise we want it to be. We've specified whether we're concerned about it being too big, too small, or just too different, where big and small are equally bad. And then we want to state our null hypothesis and our alternative hypothesis. So the null hypothesis is denoted H0, and this is the thing that you're assuming is true. So in the original example, we assumed that 70% was the true number. The alternative hypothesis really depends on whether it's a one-tailed or two-tailed test. So the null hypothesis could be that it's 70 or greater, and the alternative would be that it was less than 70. Or the null hypothesis could be that it is exactly 70, and the alternative hypothesis would be that it would be greater than or less than 70, which would mean it was a two-tailed test. Okay? So we want to assert the null hypothesis. What we're going to do is assume the null hypothesis is true, and then we're going to go through and we're going to say, what do we actually observe? And if the null hypothesis is true, how weird is what we're seeing? How unusual? Or specifically, what's the probability of seeing something that extreme? Then we're going to go through and we're going to take so this is what we're going to call a one sample t-test, and we just want to know if the mean of a sample is a certain number. And what we're going to do is calculate the mean of the sample. So we take a sample, calculate the mean of the sample, calculate the standard deviation of the sample, and then calculate the standard error of the sample. So remember, the standard deviation of the sample is the average square distance divided by n minus 1. The standard error of the mean of the sample is the standard deviation divided by the square root of n, where n is the number of observations in the sample. We did this on the sampling video, so I'm not going to belabor it a lot. If you forgot, go back and look at that video again. If you remember, William Gossett discovered the t-distribution, and it says something like the observed mean minus the actual mean divided by the standard error is distributed like a t-statistic. And in this case, we're using the same thing again. The observed mean minus the hypothesized true mean divided by the standard error of the estimate of the observed mean is distributed as a t-distribution if, in fact, the hypothesized mean is what we think it is. So we have the null hypothesis that says the mean equals some number. We use that number in there. It's distributed as a t-distribution. So the observed mean minus the hypothesized mean divided by the standard error. Calculate that amount, and this is what's called a t-statistic, and it's going to give us a number between negative infinity and positive infinity. And the t-statistic is centered, it looks like this. It's centered at 0, and so you expect, if the true mean is what we hypothesize the true mean to be, that the observed sample mean should be close to 0. It shouldn't be too big or too small. But if it's really far away from 0, then we would think, hey, that's pretty unlikely to actually happen if we have the correct mean. And we measure it in standard errors because we're trying to convert to common units. Okay, so calculate the degrees of freedom, which for a sample is n minus 1. Then what we want to do is we want to calculate the left tail. Okay, so we're going to use the t dot dist, and we want to calculate the left side. So I'm going to try to get this right because the camera is reversed from what you will actually see on the screen. So I think this will be the left side of the distribution. Remember that the t-distribution is symmetrical, so the left side is the negative side. We're doing a two-tailed test, and we calculate the observed mean minus hypothesized mean divided by the standard error, the t-statistic, and it's, say, 3.5. What we want to actually calculate is negative 3.5. And the reason we want to calculate negative 3.5 is that will tell us the percentage that's below that number. If we want to calculate the other side, then we have to do the 1 minus thing. And so it's easier just to calculate the left tail. Okay? We could say 1 minus positive 3.5, but it's easier to say calculate negative 3.5. And I'm going to show you this in a second. So just try to go along and say, okay, cool. Then we calculate the p-value. Okay, so the p-value is the probability of getting an observation, an observed sample mean that's as extreme as that. So if it's a two-tailed test, 3.5 and negative 3.5, which are probably backwards, are equally extreme. Okay, so what we want to know is the probability of being more than 3.5 away from the mean. If it's a one-tailed test, then we've already calculated the p-value. But if it's a two-tailed test, then we have to multiply the left tail times 2. So, just for example, say that we have a t-statistic of 3.47, which we're going to have in just a second, and I say, okay, the t-distribution looks like this, that tail looks like this, the left tail is 2% of that distribution. So the probability of having something that's either less than negative 3.47 or greater than positive 3.47, so just further away in either direction, is the 2% in that tail plus the 2% in the other tail, so 4%. So if it's a two-tailed test, you got to double this left number. If it's a one-tailed test, you can just use the left number, even if it's the right tail, because it's the same probability in each tail. Now we get to the last piece. What we actually do with this number is we say, okay, if this number is small, that means the probability of observing what we're actually seeing is small. And if it's smaller than alpha, we will reject the null hypothesis. So, in the first example, the null hypothesis was what the true probability of success was 70%. We said if the true probability of success is 70%, then the probability of getting 3 or less right out of 10 is 1%. 1% is less than our 5% alpha level, so we reject the null hypothesis. Okay. So we reject the null hypothesis and we say it's not 70%. We don't really know what it is, although when we calculate the statistic, we usually have a new estimate. So, for example, the new estimate, if you got 3 out of 10 right, would be 30%. So I don't know if 30% is correct, but I know 70% is wrong. Okay, on the other hand, say that the person in our example had gotten 5 out of 10. The probability of that is 15% of 5 or less. And that is not smaller than our 5% alpha level. So we would say, I'm going to fail to reject. Okay? If you fail to reject the null hypothesis, you don't accept the null hypothesis. And the reason for this is that there are other null hypotheses which might be true instead. Numerically, for example, if I got 5 out of 10 right, another null hypothesis that could be correct is that I'm 50% likely to be correct instead of 70. Conceptually, think of it this way. I might look at somebody and say, I think that person's from Texas. And I'm going to do a test. I'm just going to ask them if they pay state income tax. And if they say, yes, I pay state income tax, I can reject the null hypothesis. That person's not from Texas, because in Texas we don't have state income tax. But if the person says, no, I don't pay state income tax, does that mean they're from Texas? No, because there's other states that don't have state income tax, right? Nevada doesn't have a state income tax. I don't think Alaska has a state income tax. I'm not sure what else, but we have ruled out, New York and California, for example. Okay, but we haven't necessarily ruled in Texas. Similarly, if someone's on trial for murder and you say, oh yeah, because of if you ever watched a murder show, because of the way they were stabbed, the person's left-handed, the murderer is left-handed, and you go find somebody who's right-handed, you can say, hey, you're right-handed, and they go, yeah, I'm right-handed. Reject, you're not the murderer. But that doesn't mean the next left-handed person you find is the murderer. So you don't say, hey, that guy's left-handed, let's fry him. Right? So lots of people are left-handed. How do you know it was me? Okay, we don't. So We can reject the null hypothesis. We can say for sure this isn't right, but we don't ever accept the null hypothesis. We just fail to reject it. And we're like, oh, well, we're not sure now. There's probably a bunch of things that could also be right, but at least this one's not wrong. Now, the null hypothesis, you're usually going to go with that as your number, but you're not going to, well, you want to make sure that you don't think that it's correct so much as we just haven't proven it wrong yet. And because statistics is always a guess, so don't say, aha, I've proven this. You haven't. These are the steps. I'm going to flash the steps up here, write them down. All right. Oh, you can pause me too. So now I'm going to make them vanish. And I would like you to write the steps down all as an answer to a question. Okay, so we'll go through them again. There's 11 of them. Specify alpha, one or two sided test, state HO and HA, which are the null and the alternative hypothesis in terms of mu, where mu is the mean that you think there might exist. Calculate the mean of the sample, calculate the standard deviation of the sample, calculate the standard error of the sample, calculate our test statistic, which is our t statistic, which is the observed mean minus the hypothesized mean divided by the standard error of the estimate of the mean. Calculate the degrees of freedom, which is n minus 1 in this case. Calculate the left negative tail. It just makes more sense to do that. And then calculate the p-value. If it's a two-sided p-value, then you got to double the size of the left tail because there's also a right positive tail in addition to the left negative tail, which again, I think I'm probably backwards on the hands there. And if the p-value is less, right, less in capital letters, if it's less than your alpha value, then it's really more unlikely than you're willing to accept. And you reject. Otherwise, you fail to reject the null hypothesis. All right, let's work one. I'm going to set an alpha level of 0.05, because that's the standard alpha level. I'm going to set a two-sided test, and I'm going to have for my null hypothesis that mu equals 4. So I think the mean of this sample might equal to 4. Why? I just picked that number. But it could be, how long do people take to graduate from college? Oh, I think the mean of college graduation is 4 years. The alternative hypothesis is that mu is not equal to 4, which in this case means mu could be greater than 4 or less than 4. So I don't care if people graduate, I care. I am equally concerned if people graduate in less than 4 years and more than 4 years. If it's less than 4 years, then, I work at a university, we're not making as much money as we could. If it's more than 4 years, then maybe we're not teaching them fast enough. The alternative hypothesis is that mu is not equal to 4. We take a sample of the number of years that people take to graduate from college, and the sample is 3, 6, 9, and 2. So 3 years, 6 years, 9 years, and 2 years. We move on to calculate the mean of the sample, which is 5. We calculate the standard deviation, which we can use stdev.s, and that's 3.16. We calculate the standard error, which is the standard deviation divided by the square root of n. N is 4 because there's 4 people that we surveyed for this sample. And that gives us 1.58. So we take the observed value, 5, subtract the value that we think it is. So it's 1 bigger than we think it is. But now we have to divide that by the standard error, so we put it in terms of standard errors. So this is only 0.6324 units away from 0. So it's 0.6324 standard errors away from 0, which is actually pretty close to 0. And we're about to see how close. The degrees of freedom n minus 1, so n is 4, that's the number in the sample. 4 minus 1 is 3. Now I'm going to calculate the left tail. Okay, this is a positive number, 0.632. And I want the left tail. I know the left tail is the negative side. So I'm going to calculate the t dot dist of negative 6.324 blah, 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 comma 3 degrees of freedom, and true because I want the probability that something is less than that. So here's a picture of what it's going to look like, and I'm calculating the probability over there. I know this number is 0.632, and the t-dist formula tells me that this is 0.286. Okay, so 28.6% of the probability of mass is over there, but it's a two-sided test, so also 28.6 is above 6.32. So the whole thing looks like this, and this just isn't really unusual. So if the true amount of time that it takes people to graduate from college is 4 years, and I collect a sample, very small sample of size, and get a mean of 5, that's just not that unusual to get something more extreme than 5. Now I'm going to do another one, but I'm going to pause after each step and let you specify. So I'm going to specify these first things. I want an alpha level of 0.05. I want a two-sided test, and my null hypothesis now is that the mean equals 8. So if that's the null hypothesis and it's a two-sided test, what is the alternative hypothesis? Okay, the alternative hypothesis that is not equal to 8, which means that it's greater than or less than 8. So it's a two-tailed test. So now I go out and I collect a sample. The sample numbers are 3, 6, 0, and 2. Okay, so again, a sample size 4, 3, 6, 0, and 2. And now you need to calculate the mean. Minus 3, okay, that's 2.75. Now you need to calculate the standard deviation. That is 2.5. Now you need to calculate the standard error. That is just the standard deviation divided by the square root of n, so it's 1.25. Now you need to calculate your t-statistic. Okay, so this is the observed minus the hypothesized divided by the standard error, negative 4.4. So this is already in the left tail, so it's going to look like this. It's way over there where there's just a bitty, bitty, bitty. And I'm thinking, this is left. There's a bitty piece here. And you can just see from looking at it, that's a very small probability that's going to be left over. We need the degrees of freedom. What are the degrees of freedom? Okay, they're 3. And then we need to type the t-dist in to figure out what the actual probability is in this tail. So with 3 degrees of freedom, we type in the formula. It's t.dist negative 4.4, comma true, because we want the probability of being less than 4.4. And that gives us 0.010 blah, blah, blah. Then we have to calculate the p-value, keeping in mind whether it's a one or two-tailed test. It's a two-tailed test, so we have to multiply by 2. So the p-value, the probability of getting something more extreme than negative 4.4, which is less than negative 4.4 or greater than positive 4.4. So it's either tail of the distribution here. That is 2 times 0.10, which comes out to be 0.217. Okay, so we have our p-value now, the probability of getting a result at least as extreme as the one we're actually observing, and it's about 2%. Our alpha value is 5%. So what do we do? Okay, the p-value is less than the alpha value, so we reject the null hypothesis. So the null hypothesis is that mu equals 8, and we say, no, this is too far away from 8, 2.5 is too far away from 8. It's possible if the true value is 8 to get a weird sample, but it's very improbable. In fact, the probability of getting such a sample is 2%, which we calculated. So we're going to reject the null hypothesis and assume, instead of the fact that we got a weird result, we're going to assume that our hypothesis about mu was in fact incorrect. Okay, so in one case we failed to reject, and in another case we rejected. All right, I'm going to have you do one from start to finish. Again, all you have to do is follow through the steps, and then just remember, I want things that, if something's highly unlikely, then I'm going to reject the null hypothesis and assume that that hypothesis is wrong, rather than that we got really weird luck. Now, I would like you to work one all the way through. So I'll give you the starting parameters, and I'm going to have you do all the rest of the steps. So again, we're going to use an alpha value of 0.05 or 5%. Again, we're going to do a two-sided test. And in this case, the null hypothesis is that mu equals 10. And the sample is going to be 12, 9, 11, 9, 8, 10. So there's 6 observations in the sample. So starting with calculating the alternative hypothesis, or specifying what the alternative hypothesis is for a two-tailed test, given what we know about the null hypothesis, calculate all that stuff. All right, so for the first step, if the null hypothesis is that mu is equal to 10, and it's a two-sided test, the alternative hypothesis is that it's not equal to 10. It's either greater than 10 or less than 10. We don't care. We're just interested in whether or not it's 10. So next thing to do is calculate the mean of the sample, which is 9.8333333333, and then we calculate the standard deviation of the sample using the standard dev.s formula, and that comes to be 1.47196014. Then we calculate the standard error of the estimate of the mean, and that's just the standard deviation of the sample divided by the square root of n. In this case is 6. We have 6 observations, so the standard error turns out to be 0.600. Okay, now we got to calculate our t statistic, which this is going to tell us in standard errors how far away what we're seeing is from what we expected to see. And that's observed minus hypothesized divided by standard error. If we do that, it's negative 0.27773501. And then we need the degrees of freedom to put in the formula. It's n minus 1, so n is 6, the number of observations, and 6 minus 1 is 5. Now we calculate the left tail. So our t-statistics are already in the left tail, so it's all this stuff over here. What percentage of the probability mass is over here, and that's t dot dist. Don't forget the dot, because if you do t dist, it calculates it in a totally different way. Negative 0.277, comma 5, which is the degrees of freedom, comma true, because we want the probability of having less than that, or the probability of being further away than negative 2.7, negative 0.27. And that gives us 39%. So 39% of the probability mass is over there, but it's a two-tailed test, so we would also be concerned of how odd it would be to get a number that was positive 2.77 or greater. So we multiply that left tail by 2, and we're looking at all this probability mass, and it turns out that there's about an 80% chance, a 79% chance that we would have an observation at least this extreme, or more extreme, that if the true value was 10, which isn't surprising because the true value is 10 and the measured value is 9.8. So that doesn't seem very strange to me. We have a p-value of 0.79, which is much larger, so it's much more likely to occur than our alpha value of 5%. So we fail to reject the null hypothesis. We don't accept the null hypothesis because the true answer could be 10.1 or 9.9, but we do fail to reject it. So if anyone wants to get into a fight of whether it's 10, you don't want to get into that fight. We're going to do one more, and I'm going to change things up a bit. And first thing I'm going to do is I want to change the alpha value to 10%. So I'm going to say, look, if there's a 10% chance of getting something this extreme or more extreme, then I want to reject the null hypothesis. So I want to be a little bit more liberal in my interpretation. And I actually want a one-sided test. So in this case, sort of my conceptualization here is we've been testing all these people to see if they're 70% accurate. I want to see if our own people are 70% accurate. So I'm going to go survey some of our own people to see how accurate they are. And I'm only concerned if they're less accurate. So the null hypothesis is that their accuracy is 70 or above. So mu is greater than 70. So this is a one-tailed test. So you're going to have to specify the alternative. But first, let me give you what the sample is. So I go out and collect from 3 of our people, and I find 65, 61, and 54. So I'm going to try to be as generous as I can, but I want to know if our guys are 70% correct. So you go through, specify the alternative hypothesis, and then do all the rest of the steps, keeping in mind you now have an alpha value of 10%, and it's a one-sided test. And we're only interested, well, you have to figure out what we're interested in, I suppose. Okay, go for it. All right, so our null hypothesis is that mu is greater than or equal to 70. And our alternative hypothesis is that mu is less than 70. Our sample is 65, 61, 54. That gives us a mean of 60. So on average, our guys are coming up with 60, or girls, or folks, or non-gendered people. Anyway, 60 is what our people are coming up with. The standard deviation of that is 5.567. That's the standard deviation of our sample. And the standard error of the mean of the sample is the standard deviation divided by the sample size, which is 3, the square root of the sample size, which is 3. So we get standard error of 3.937. Okay. Now we calculate our t-statistic, and that's the observed minus hypothesized divided by the standard error. You type all that stuff in, you get negative 2.54, and then some zeros. And then we need the degrees of freedom to do our test. 2 degrees of freedom because there's 3 in the sample. And we're going to calculate the left tail. So what's the probability of seeing something that is negative 2.54 or less? And we type that in. It's t.dist, negative 2.54, comma, 2 degrees of freedom, comma, true. And that gives us 0.063. Okay, so about 6% chance of seeing something this extreme or more extreme if our null hypothesis is true. Now, we calculate the p-value. In this case, we don't have to do anything to it because we don't care about the right-hand tail. We don't care if people are more than 70. So I only want the 10% on the bottom. And so our p-value then is 6%, 0.06, and our alpha value is 0.1. So our p-value is less than our alpha value, which means that we would reject the null hypothesis. So the probability of this happening is something that's extreme happening is 6%, and we were only willing to go with it if the probability was 10% or less. We reject the null hypothesis and say that, yeah, our average isn't 70. I'm not quite sure what it is, but it's not 70, so maybe we should quit giving other people the test for 70. Although maybe that's why we want to hire people that can do better than 70, because we've hired people that can't do better than 70 in the past. Okay, so what are we going to do with this? There's just some steps. You got to go through and make a couple of calculations. The important thing is to get the concept down. If something's too improbable, right, so we assume that we know what mu is, and we calculate the probability of observing what we're actually observing, or something more extreme than that. And if it's just too improbable what we're seeing, we reject the null hypothesis that our mean's what we thought it was going to be. All right? So that's the concept. This is how you go about doing it. Now, there are lots of different t-distribution, t-tests. We've done, this is kind of the simplest one, what's called a one-sample t-test. We have just one sample, and we have a specified, pre-specified mean that we're testing against. This is a hypothesis. You could do a two-sample, so maybe you surveyed men and women, and you want to know if there's a difference between men and women. Then you don't have a pre-specified mu, but you basically do the same thing, and you're going to get the observed for the men versus the observed for the women divided by something called the pooled standard error. And that's where it gets a little bit complex, because you have to figure out how to make the standard errors go together, and you have to decide whether both groups have the same standard error and stuff like that. But the important thing is, it's still the same sort of thing. You've got one observation, another observation, and you divide by some number, which you can go look up at how to calculate that number. And that's distributed as a t with some degrees of freedom, which you can also look up what the degrees of freedom are based on your sample sizes. And then you can say, yeah, if these two things are equal, I wouldn't expect them to be this far apart. Or they're close enough together where I can't say that they're not equal. Okay? And you can do that with two different types of samples. You can do that with paired samples, where you have like a group of people and you survey them before and after, or test one, test two, or something like that. You can have different sizes of samples, and all that actually gets done in Excel through something called t.test. And you can look that up if you want. We're not going to do it. The important thing is to keep in mind that if you want to do a hypothesis test, what you're going to do is you're going to say, how improbable is what I'm seeing if my hypothesis is true? And if it's very improbable, you reject your null hypothesis. Now, there's an alternative way to do this. The alternative way is basically go through the same steps, except instead of calculating a t-statistic, you calculate a confidence interval with the 100 minus alpha. So we calculate 90% confidence interval. That will correspond to a 10% alpha level. And if the number you're interested in is in that confidence interval, then you fail to reject. If the number is outside that confidence interval, then you reject. So, for example, if I want to do this last one, my confidence interval, say my confidence interval is 1 to 7, and the number the hypothesis I want to test is 5. Well, 5 is in between 1 and 7, so I would fail to reject it. If, on the other hand, it was 10, the hypothesis I wanted to test, 1's not between 5 and 7, so I would reject it. So confidence intervals and hypothesis tests come in together. This also helps explain why we don't accept the null hypothesis, because anything in that confidence interval we would fail to reject. Okay, the important thing is you can do some of these by following the steps, A, and B, you understand what we're getting at with these hypothesis tests, because we're going to be doing hypothesis tests. And I just want you to understand in your soul what's going on. The computer's going to calculate all this stuff for you, but you can understand better if you actually do it yourself. All right, if you have questions, contact me. Send me your work. I really can't do anything to help you if you say, hey, I missed question number 2. Why did I do that? Why did I miss it? And I say, oh, because you put 7 for your answer, and the answer was 8. That's not helpful. But if you send me your work, say here's step 1, step 2, step 3, I can say, hey, in step 3, you added when you should have subtracted. Or in step 4, you got the signs confused, or something. I can figure it out if you send me your work. So send me your work, and I will help you. If you have questions, contact me. But hopefully we can just go through these steps and you can get it done and in your soul start understanding it. All right, thank you.